Welcome to the presentation on the indefinite integral or the antiderivative. So let's begin with a bit of a review of the actual derivative. So if I want to take the derivative dx, it's just the derivative operator. And if I want to take the derivative of the expression x squared, this is an easy one if you remember the derivative presentation. Well, this is pretty straightforward. You just take the exponent, that becomes the new coefficient, right? You actually multiply it times the old coefficient, but in this case the old coefficient is 1, so 2 times 1 is 2. And then you take the variable 2x, and then the new exponent will be 1 less than the old exponent. So it'll be 2x to the 1, or just 2x. So that was easy. If I had y equals x squared, we now know that the slope at any point on that curve, it would be 2x. So what if we wanted to go the other way? Let's say if we wanted to start with 2x, and I wanted to say 2x is the derivative of what? Well, we know the answer to this question, right? Because we just took the derivative of x squared and we figured out 2x. But let's say we didn't know this already. You could probably figure it out intuitively. How you can kind of do this operation that we did here, how you can do it backwards, right? So in this case, the notation, well, we know it's x squared, but the notation for trying to figure out 2x is the derivative of what, we could say that, let's say 2x is the derivative of y. Whoops, of y. So 2x is the derivative of y. All right, let's get rid of this, of y. 2x is the derivative of y. Then we can say this. We can say that y is equal to, and I'm going to throw some very fancy notation at you, and I will explain it more actually I'll explain why we use this notation in a couple of presentations down the road, but you just have to know at this point what the notation means, or what it tells you to really do. It's really just the antiderivative or the indefinite integral. So we could say that y is equal to the indefinite integral of 2x dx. And I'm going to explain what this squiggly line here is in dx, but all you have to know is when you see the squiggly line and this dx and then something in between, that you really, all they're asking is they want you to figure out what the antiderivative of this expression is. And I'll explain later why this is called the indefinite integral. And actually, this notation will make a lot more sense when I show you what a definite integral is. But let's just take it for granted right now that an indefinite integral, which I just drew here, it's kind of like a little squirrely thing, is just the antiderivative. So y is equal to the antiderivative, essentially, or the indefinite integral of the expression 2x. So what is y equal to? Well, y is obviously equal to x squared. But let me ask you a question. Is y just equal to x squared? Because we took the derivative, and clearly the derivative of x squared is 2x. But what's the derivative of x squared? What's the derivative of x squared plus 1? Well, the derivative of x squared is still 2x. And what's the derivative of 1? Right, derivative of 1 is 0, so it's 2x plus 0, or still just 2x. Similarly, what's the derivative of x squared plus 2? Well, the derivative of x squared plus 2, once again, is 2x plus 0. So notice, the derivative of x squared plus any constant is 2x. So really, y could be x squared plus any constant. And for that any constant, we put a big C there. So x squared plus c. And you'll meet many calculus teachers that will mark this problem wrong if you forget to put the plus c when you do an indefinite integral. So you're saying, Sal, okay, you've showed me some notation. You've reminded me that the derivative of any constant number is 0, but this really doesn't help you solve an indefinite integral. Well, let's think about a systematic way, if I didn't do it for you already, that we could solve an indefinite integral. Let me clear this. Make it black again. Let me make a bolder color, I think, would make this more interesting. So let's say we said y is equal to the indefinite integral of, let's say, let me throw something interesting in there. Let's say is the indefinite integral of x cubed dx. So we want to figure out some function whose derivative is x to the third. Well, how can we figure that out? Well, just from your intuition, you probably think, well, it's probably something times x to the something, right? Well, let me write it. So let's say that y is equal to a x to the n, right? So then, what is dy dx? Dy dx, or the derivative of y, is then, well, we learned this in the derivative module. You take the exponent, multiply it by the coefficient, so it's a times n, and then it's x to the n minus 1, right? Well, in this situation, we're saying that x to the third is this expression. It's the derivative of y, right? This is equal to x to the third. So if this is equal to x to the third, what's n, what's a, and, well, yeah, what's a and what's n? Well, n is easy to figure out, right? N minus 1 is equal to 3. So that means that n is equal to 4, right? And then what is a equal to? Well, a times n is equal to 1, right? Because we just have a 1 in this coefficient. This has a starting coefficient of 1. So a times n is 1. If n is 4, then a must be 1/4, right? So just using this definition of a derivative, I think we now figured out what y is equal to, right? Y is equal to 1/4 x to the fourth. I think you might start seeing a pattern here. Well, how did we get from x to the third to 1/4 x to the fourth? Well, we increased the exponent by 1, and whatever the new exponent is, we multiply it times 1 over that new exponent. So let's think if we can do a generalized rule here, that the indefinite integral, and of course, plus c. I would have failed this exam. So let's make a general rule that if I have the integral of, well, since we already used a, let's say b times x to the n dx, right? What is this integral? This is an integral sign. Well, my rule is I raise the exponent on x, right, by 1. So it's going to be x to the n plus 1. And then I multiply x times the inverse of this number. So times 1 over n plus 1. And of course, I had that b there all the time. And one day I'll do a more rigorous proof, and maybe we'll be vigorous as well as to why this b just stays multiplying. But actually, I don't have to do too rigorous of a proof. If you just remember how a derivative is done, you just multiply this times the times the exponent minus 1, right? So here we multiply the coefficient times the 1 over the exponent plus 1, right? It's just the inverse operation. So let's do a couple of examples like this really fast. I have a little time left. I think when the examples, at least for me, really hit the point home. So let's say I wanted to figure out the integral of 5x to the 7th dx. Well, I take the exponent, increase it by 1, so I get x to the 8th, and then I multiply the coefficient times 1 over the new exponent. So it's 5/8 x to the 8th. And if you don't trust me, take the derivative of this. Take the derivative, d dx, of 5/8 x to the 8th. Well, you multiply 8 times 5 over 8. Well, that equals 5. X to the, and now the new exponent will be 8 minus 1, 5x to the 7th. And it applies to, and of course, plus c. I don't want to forget the plus c. So I think you have a sense of how this works. In the next presentation, I'm going to do a bunch more examples, and I'll also show you how to kind of reverse the chain rule. And then we'll learn integration by parts, which is essentially just reversing the product rule. See you in the next presentation.